Hello everyone, welcome to aplusbi. This channel is all about complex numbers, and in this video we're going to be solving a radical equation with complex numbers. Now we have the square root of z plus the square root of negative z equals 2, and we're going to be solving for z values. I understand this type of notation could be a little abusive because, or I should say abuse of notation, because a complex number has two square roots. So which one are we talking about? Let's find out. Okay, and we're also going to plug in our answer at the end to see what is going on with the two way of finding square roots. So first method. For my first method, I'd like to square both sides, because why not? If you square both sides, you're going to get something nice from here, because the radicals are going to disappear for the most part. We're going to get z plus negative z plus 2 times the square root of z times the square root of negative z equals 4. Awesome. Obviously, z and negative z are opposites, so their sum is always 0, even if they are complex numbers. Now, we end up with something like this. How do you multiply the square root of z and the square root of negative z? Well, you can just multiply them, even though that's kind of problematic. And again, we'll talk about this issue. But we get the square root of negative z squared equals 4. And upon division by 2, we end up with the square root of negative z squared equals 2. Great. Now at this point, we're going to go ahead and square both sides. Why? Because we want to get rid of all the radicals and we want to end up with polynomials. When we square both sides, we're going to end up with negative z squared equals 4. And of course, if you multiply both sides by negative 1, you get z squared equals negative 4. This is what makes z really complex, or should I say imaginary. Okay, now how do you find z from here? Easy. Think about a number whose square is negative 4. It's 2 and negative 2, right? No, that's not the answer, because if you square them, you get positive 4. To get negative 4, you have to add the imaginary element, which is I. In other words, 2i squared will be negative 4. But why is that so? And can we find it kind of like a little bit of algebraically or using Euler's formula? And absolutely. If you think about how you can write 4 as a complex number, first of all, it's on the negative real axis, right? 4 units away from 0, so it's going to be here. And the angle it makes can be described as pi radians, and of course you could add multiples of pi to it, but let's just stick with pi for now. So I can write this as, and by the way, what is the modulus? R will be 4, right? It's distance from 0. It's going to be like 4 times e to the power I times pi. You see, Euler's formula allows us to write a complex number as e to the power I theta, which could also be written as cosine theta plus I sine theta, but that's a different story. Okay? Now, from here, taking square roots is so easy. Let's just take one, and then the other one will be the opposite, because they're opposites, right? Hopefully you know that. Z is equal to 2 times e to the power. Now, to raise this to the power 1/2, I need to cut the angle in half. So that's going to give me I times pi over 2. Actually, if you consider pi over 2 as our angle now, that represents our imaginary number I. But with a 2, that's just going to be 2i. Make sense? So one of the solutions will be 2i, and of course you could call that z sub 1, and z sub 2 will be the opposite, negative 2i, because there are two numbers whose square is negative 4, and those numbers are 2i and negative 2i. Make sense? Okay, so that's going to be the solution set, basically. All right, so let's go ahead and take a look at the second method, and we're going to talk about some, ambiguity here, kind of go into a little deeper. So the second method, again, the original problem was square root of z plus the square root of negative z equals 2. Maybe a better way of writing this problem without abuse of notation would be z to the power 1/2 plus negative z to the power 1/2 equals 2. Would that make a huge difference? Yes, because when you say 1/2, you're talking about the complex roots of z, and there are two of them. So this is kind of like, this is a multi-valued expression. That's why we got to be very careful, but I'm not being careful anyways. So the second method is going to involve the following. Negative z can be written as z times -1. So I'm going to write it as -1 times z, like this, and separate them. And then square root of -1 can be written in two ways, because -1 has two square roots. If you're thinking about the complex world, you have to be very careful. You have to make that distinction. But anyways, let's just go with one of them first. I guess I could call this I. So we get square root of z plus I times the square root of z equals 2. And then factor out square root of z. You're going to get 1 plus I is equal to 2. Great. Now let's go ahead and divide both sides by 1 plus I. And then consider the conjugate, which is 1 minus I. That should give you 2 minus 2i divided by 2, which is 1 minus I. And then if you square both sides, here's the thing. A complex number has two square roots, but if you know the square root of a complex number, then there's only one number whose square root equals that number. Does that make sense? So from here, we only get a single solution. How is that possible? We're supposed to get two. I'll tell you. So z from here is going to be 1 minus I squared, which is 1 minus 2i plus I squared, but I squared is -1, so z can be -2i. Remember, when we said that, oh, the square root of -1 is supposed to be I, actually, that was partially true because it could also be -I. If it's -I, then we get square root of z minus I times the square root of z equals 2. And then from here, you're going to get something similar, but this time it's actually going to be 1 plus I. And when you square it, you're going to get 2i. Yay. So again, we're getting the same solutions as before. And of course, right? I mean, it should be the exact same thing. But here's the problem. Here's the problem. Now, we know that z is equal to 2i, right? So we can kind of plug it in to make sure that it satisfies the equation. Is it true for z equals 2i? We can just test one of these. You don't have to test both, but if you do want, definitely. Now, if you plug it in, this is going to be the square root of 2i, and this is going to be the square root of -2i. Here's the problem. 2i has two square roots, and -2i has two square roots. So let's go ahead and take a look at the alternatives. The square root of 2i is 1 plus I, and its opposite, which is -1 minus I. The square root of -2i is 1 minus I, and its opposite, which is 1 plus I. So, when I add these two quantities, I kind of need to think this way. I can pick anything I want because it wasn't specified. Like, you can't specify. When I say square root of 4 in real world, it's 2 for sure. But when I say the square root of 4 in the complex world, there are two values. So which value are we using, right? So I could take the first one to be 1 plus I. And then instead of picking 1 minus I, because I don't have to, I could use -1 plus I, right? But then this is going to be 2i, and it's not going to work. It's not equal to 2. But guess what? At least we know there is a pair that satisfies this. So that's the problem here. And let's go ahead and take a look at the result from Wolfram Alpha. Hopefully that'll confirm our findings. And yay! This brings us to the end of this video. Thanks for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe, take care, and bye-bye.